FAQ is a class where you learn a bunch of things to solve differential equations, and there's not a heck of a lot of theory on this.
Sounds like
Theory.
Yeah, that's like calc.
Calc gets a heck of a lot of theory. These are theory of different equations. Just don't get a lot of it.
Oh, so you want to give us more?
It's more of you look at a problem and know what formula Yes. Got a new homework assignment for you. Because of course I do. Everybody's so impatient. Let's do it at the end of the hour.
25.
Yes, it's 25. Yep. It's 4 problems. Tuesday or Wednesday, whatever. You can schedule it with me. Since we had so many people not bother coming in at 6, they were coming in at a different time. So just tell me what time you plan on coming in. 6 is fine. Just tell me a time on Tuesday or Wednesday. But you do have to start it before noon on Wednesday because I have class at noon and then I'm leaving town. So.
Before noon on Wednesday?
Yeah.
So.
I could theoretically take it right after
In
this
case you didn't see the email, there's a review session on Monday, 8:30 and 10.
Everybody here, hang on. Review session Monday, UC 144?
Yeah.
Yeah. 8:30?
You just had to make it right around one.
When?
Sorry.
No,
You
you're
said
not.
you have to like be done by 12 or start?
You have to start it before I leave. It's later.
I'm highly contemplating just taking it out Wednesday. I'm
gonna do it at 10 o'clock on Wednesday, Michael.
I can't. I got the contest.
Just tell me, just email me when you plan on coming. I mean, I'll be here Tuesday night anyways. If you want to just do it at 6 on Tuesday, that's fine. It's just that I think everybody but like 3 people showed up at a different time last time, so just tell me when you plan on coming in. That's all I really care. All right. Questions about anything before we get going? No. All right. Well, let's continue to our discussion with continuous distributions. Do a few more problems. Pardon me, goodness. Do a few more problems and then talk about a couple of specific types of continuous distributions. So this is problem number 3.3-24 in your book. So it says the time x to failure of some computer, or a component. If I can spell the word electronic. Has a PDF of, this is the important part, f of x equals 2x over 1,000 squared, e to the minus x over 1,000 squared, 0 less than x less than infinity. So it tells you the support is from 0 to infinity, which makes sense if x is going to be, pardon me, a time until failure. Certainly can't have a negative failure time. At least it's more challenging to have a negative failure time. So the first part just asks us to compute the probability that x is greater than 2,000. So if we're going to do this, what would we want to set up to calculate this probability? Just using the stuff that we talked about last time. What do we need to do to set up how to find this probability?
First expression, what is the number that's
In the exponent?
Yeah.
It's x over 1,000. Better? It's 1,000 squared on the bottom. Yeah. There's a reason why it's written that way. So what do we need to do here? Take the, I'll do the integral, right? From 2,000 to, yep, to infinity, right? We want x is greater than 2,000, so I'll do 2,000 to infinity of what? The PDF, good. Pardon me. Right? If we're going to calculate a probability, we just do an integral in this case, right? Integrate over the interval that we want the probability for, and we integrate our PDF. What technique are we going to use here to integrate this? No. Is it u substitution? What are you going to let u equal? Yeah, let u equal the exponent. What's the derivative? Oh, the derivative will be, the derivative is the negative of this thing sitting out in front, isn't it? Right? With the square in it, exactly, because this is x squared over 1,000 squared. So when you take the derivative, you get 2x over 1,000 squared. That's why they wrote it that way. So we're essentially doing the antiderivative of what? Oh, I'll just write it out. So we'll let u equal negative x over 1,000 squared. du is negative 2x over 1,000 squared dx. So I need to adjust for the minus sign, right? Got to adjust for this minus sign here. So I'll need a negative. This just becomes what? What does your integrand become then? E to the u du. I also need to adjust the limits, right? We agree? All right, when we put in 2,000 for x, what is u? Well, if I put in 2,000 for x, though, what do we get? Yeah, we get 2 squared, right? So we get negative 4. And then as x goes to infinity, what does u go to? Negative infinity, right? So we have negative the integral from negative 4 to negative infinity of e to the u du. Everybody okay with where I got the limits? Literally just plugging in the endpoints of the integral, right? Plugging in the limits of integration into the formula that we have for u, right? So we're going from negative 4 to negative infinity, which seems backwards, doesn't it? Okay, but remember, we put them in the same relative spots, right? 2,000 was the lower limit, negative 4 is the lower limit. Infinity was the upper limit, so negative infinity is the upper limit. But we also have the negative sign out in front. What do we know a negative sign does with respect to the integral? Flips the limits, right? So I might as well do that. This is just going to be the integral from minus infinity to minus 4 of e to the u du. Is that better? Makes you feel better. It doesn't, at least makes me feel better. Okay? And that's all what it's all really about, is making sure I feel fine. Okay. Antiderivative for e to the u. E to the u. All right. When we put in negative 4, we just get e to the negative 4. If I let u go to negative infinity, what does e to the u go to? 0. So this is just e to the negative 4. Questions on that one? Yeah.
So we don't like in calculus how we did
The limit?
B and
Yeah.
stuff. We don't gotta do all that.
No. Just know that you are taking a limit here. I'm be a little bit more lax with the notation as far as that goes. I mean, you do need to understand that you really are taking a limit. I'm not. I don't want to see an e to the minus infinity in the problem because that doesn't make any sense. But understand that you know that you're taking a limit. That's the important part. This one okay? We could have done this one in a little slightly different way had we had a function that was defined in terms of the PDF to start with. And this is what we refer to as the cumulative distribution function. So the definition of the cumulative distribution function, we use a capital letter to denote the cumulative distribution function part. So by definition, what the cumulative distribution function is, it's the probability that your random variable is less than or equal to whatever this input is. So this is why we call it cumulative distribution function. So it accumulates all the probability up until a certain point. Okay. So it's accumulating probability from the lowest possible x value, whatever that happens to be, up until a certain point. We could have done this for discrete distributions as well. Just in discrete distributions, it would be a summation rather than a integral that we're going to do here. And we would have jumps, right? I'll show you what I mean in a minute for a discrete distribution. Okay. But in this case, all we're doing is accumulating probability up until a certain point. So if we have a continuous random variable, this would be the integral from whatever your lowest x value is. So I'm just going to put minus infinity, even if it doesn't make any sense for the support for the variable, because it might be that this is below where the support is, up until some value of x of the PDF of x. Capital X. Okay, so this is how you calculate a cumulative distribution function for a continuous random variable. Again, the only reason why I put the lower limit as minus infinity here is I want to go from as low a value of x as I can up until the x value, where this x is going to vary. So in this particular problem, for the previous example, if I wanted to do the cumulative distribution function for the example we just got done with, what was the lowest possible x value? 0, right? So I would do the integral from 0 to x, because that was the lowest possible x value, right? It went from 0 was less than x was less than infinity. And what we assume for PDFs is if it's not defined for certain x values, we assume it's 0. So it told us what the PDF was on 0 to infinity, so everywhere else is going to be 0. If I integrate 0 over an interval, I'm still going to just get 0. Does that make sense? So I only need to worry about starting this at 0. Our PDF was the 2x e to the minus, or 2x over 1,000 squared, e to the minus x over 1,000. Whoops, change that to a t. E to the minus x over 1,000 squared. The reason I'm writing it with t's rather than x's is because where did I put the x in this problem? It has no limit of integration, right? The variable being in the limit of integration has absolutely nothing to do with the variable that's in the integral. So just from a form standpoint, we write it with a different variable. But going back to what we did up here, if I ignore the limits of integration here, I already know what an antiderivative is. It was minus e to the u, right? And an antiderivative would be minus e to the u, correct? So I could go back up here and do this rather quickly. This would be minus e to the minus t over 1,000 squared, evaluated from 0 to x. We already did the u substitution before, right? If I ignore the limits of integration, we were integrating minus e to the u. The antiderivative would be minus e to the u. So that's all I'm writing there, right? I'm just not reinventing the wheel and redoing the distribution, or sorry, the u substitution. All right, so if I plug in x, I'll get x over 1,000 squared. If I plug in 0, I'll get 0 here, right? But e to the 0 will be 1. So if we plug things in there and rearrange, you'll get 1 minus e to the negative x over 1,000 squared. So this is our cumulative distribution function. So again, by default, the cumulative distribution function gives you the probability from lowest possible x value up to a certain point, right? So let's go back and revisit the problem that we just did. Pardon me. We were looking at the probability that x was greater than 2,000, right? We agree? Can I rewrite this as a probability statement where I can use the cumulative distribution function? Can I rewrite this in terms of a probability where x is less than or equal to something? Yeah, I can do 1 minus, right? I can do the complement, can't I? So this would be 1 minus the probability that x is less than or equal to 2,000, right? We agree? That's just a complement statement, isn't it? That's nothing new. Okay. The new part is that this second piece here is the definition of the CDF, the cumulative distribution function. Right? This is the definition. So this is just f of 2,000. Capital F of 2,000. With the parenthesis actually closing off the function notation. Right? So I can just plug this 2,000 now in up here where we found our CDF and get the same answer. This will be 1 minus e to the 2,000 over 1,000 squared, which will just give me e to the negative 4, like we had before. Pardon me. Yeah, Megan.
So that function you just found, that's not a general function, that's specific for this problem?
This function here, you mean? This was specific to this problem because that was the PDF. But in general, by calculating it this way, this is the general rule for finding any. So this is the general rule. This was just specific to the problem we just did. So if you're given the CDF, the cumulative distribution function, you can get answers quickly rather than having to go through an integral, if you already have it. Now, to get it, a lot of times you have to have the integral. But the whole point of this is, in some problems that we do, we'll know what the CDF has to be based on the type of distribution that we have. So some of the problems you can make go faster by using the CDF rather than integrating the PDF every time. And we'll see that as we go through some more examples. Okay. Another thing the CDF can help us with is actually what's part B in this problem. Part B in this particular problem says determine the 75th percentile. The notation they use for percentiles is a pi and then a sub, whatever the percentage is, the decimal is for the percentage. So pi sub 0.75 is the 75th percentile. So just a little bit of review, or new, I suppose, if you haven't heard it before, what percentile is. When we want to know whatever percentile we have, so I'll say it's pi sub k, whatever this is just the probability that x is less than or equal to k, not b, k. So what the 75th percentile says is it's the x value where 75% of all x values are less than that. So for example, if you take a standardized test and you're at the 75th percentile, that means 75% of the people did worse than you. That's what that percentile means. Does that make sense? Okay. So notice that this is tied to figuring out, that's right. This pi sub k, this is tied to being able to figure out what this k value is, right? Right? Whatever this number happens to be, that's what this I wrote that wrong. Sorry. Nope. This isn't equal. That's not equal. This k goes here, right? So pi sub k is the thing that's up here. I lied. Those are not equal to each other. This little k that's in the subscript. Yeah. No, I did that wrong again. Sorry. Pay no attention to the man behind the curtain. Try that again. One more time. I'll get it right. I know how to do the problem. I'm just not doing the notation right. Sorry. I think I had looked at it before class, and I did. All right. The notation is that the probability is in the subscript. Right? The probability is in the subscript. Correct? So this subscript needs to be equal to this probability. Right? This pi sub k is the actual x value that we want, which is why it's going up here in the interval. Now, the whole point of this was to get down to the point where we need to solve an equation. The right-hand side looks like what? What did we just define? That's the cumulative distribution function of this value, right? So the right-hand side is f of pi sub k, and we want to set that equal to the k. And we want to solve this equation. That's how we find percentiles. Your cumulative distribution function calculates the probability that x is from the lowest possible point up to a certain value. We want to know where the value is so that whatever that percentage is below that value. So we have an equation to solve. I apologize for writing it wrong, not once but twice. Okay. So going back to this problem, it says determine the 75th percentile. Well, we know what our CDF is. It was 1 minus e to the negative x over 1,000 squared, right? That's the CDF. What do we want that to equal? What percentile are we looking for? Yeah, well, I said it equal to 0.75 because we're looking for the 75th percentile, right? There's nothing special about 0.75. It just told us to find the 75th percentile. Or what you would call the third quartile, because it's up at the 3/4 point of the distribution. So in this case, you would just manipulate, do some algebra, right? E to the minus x over 1,000 squared equals 0.25. Right? Just flip-flop sides. What do I need to do to get rid of the e? Natural log. Right? And then I need to move the negative over, take the square root and multiply by 1,000. So this would give me x is equal to the 1,000 square root of the natural log of 4. 0.25 is 1/4. If I put the negative out in front of the log, I can move it up as the exponent. I get a 4. Whatever that value happens to be.
Can you say that one more time?
Say again?
Can you say that one more time when you got that on 4?
0.25 is 1/4. So 1 over 4. If I move the negative over to the other side and then move it up as an exponent. Yeah. I did it that way because I really don't like seeing a negative under my root. Because otherwise I would have had the square root of negative log of 0.25. And not that it was wrong, it bothered me. Yeah, Megan, or Morgan. Sorry. You're right side by side.
Where's the left side of your equation?
Which one?
Like the left side, the 1 minus e.
That's the cumulative, that's our definition of the cumulative distribution function in this problem. That was what we found when I did the example of finding the CDF.
Yeah,
That was the CDF
for that problem.
for that problem. So I just set the CDF equal to a 0.75.
So then where's like the pi sub k?
The pi sub k would be your x. I just wrote x because I didn't feel like writing pi sub k all the way through.
So would the 50th percentile be our mean?
No, right. You're right. You're thinking about the right thing because you said low more. 50th percentile would be low. That's the mean. So median. That's how you find the median. Is you just set equal to 0.5. You got a head against this. Good question. You didn't need me to. Yeah, so if you have a problem that asks you to find the median is where the distribution gets split in half, 50% or below, 50% above. So if you're asked to find the median, you would do a similar computation. We just said equal to 0.5 and solve for the x. Find the median. So that's one that gets asked actually quite a bit in the homework or different types of problems. So if you're asked to find the median, you would set your cumulative distribution function equal to 0.5 and solve it for x. Again, median means split the data in half, split the distribution in half. 50% below, 50% above. So that's why we're setting it equal to 0.5. It's a question, Grace. Questions on that at all? So hopefully, as you looked at the definition of the CDF, you should see a relationship, a more of a calculus idea relationship between the CDF and the PDF. Notice that the CDF is defined as an integral of the PDF. So if I differentiate both sides, when I take the derivative of the CDF, what should I get? What happens when you differentiate an integral? it's just a function on the inside, right? As long as some special conditions are met. Technically speaking, this should be a constant, not a minus infinity, but there's a reason why that we just get f of x for this being going off to negative infinity. Because this integral, when we do this improper integral, it has to converge, right? When I integrate the PDF over the entire support, I have to get 1, right? I have to get a I know I'm talking about calculus too, but I have to get a convergent improper integral. There has to be a finite amount of area under the function, right? The only way you can get a finite amount of area under the function is at worst, it pinches down to the x-axis really, really fast. It doesn't actually have to cross it and become 0 eventually, but it does have to pinch, right? When you did all your improper integral stuff, to make it converge, it had to get down there fast enough. Well, that means the function is getting closer and closer and closer to 0 really fast. So if I do the derivative, it's going to have to be 0 there. It has to be really, really flat. Right? So I had to get a 0 there. That's the first part. If this were a function of x rather than just an x, then you would have a derivative of the inside for a chain rule idea. But let's get into that next time. You don't have to worry about all those technical details. This is the relationship between your CDF and your PDF. However, as you go through more math classes, you should worry about technical details. The math is in the details. That's the whole point. All right. So that's the connection between CDF and PDF. We did this for continuous. There's not this nice connection for discrete, because in the discrete case, you get a bunch of jumps. So what I mean by that is, as an example, let's say you had just a discrete random variable that will look like this. So let's say I defined the PDF by a table. So the probability that x is 0 is 0.2, the probability that x is 1 is 0.1, x is 3 is 0.5, x is 7 is 0.2. If I wanted to do the CDF in this case, well, first I'm going to have to define it as a piecewise defined function because of all the jumps. All right. Until I get to 0, what's my cumulative probability? If I think about coming along from negative infinity up to 0, until I get to 0, how much probability have I accumulated? 0, right? So this will be 0 for x less than 0. Once I hit 0, what does the probability jump up to? 0.2. How long does it stay 0.2? Until we get to 1, right? What happens when we hit 1? It jumps to, we're doing cumulative, right? So it's going to jump to 0.3, right? We have to add the 0.1 to it. Remember, this is a cumulative idea, right? We haven't accumulated anything until we hit 0. Then it jumps to 0.2. We don't accumulate anything else until we get to 1, but we're accumulating, so we add the 0.1. How long does it stay at 0.3? Until 3. What happens when we hit 3? Because the 0.8, because we jumped another 0.5, right? Does that make sense? How long does it stay at 0.8? Until 7, and then what happens at 7? It becomes 1. And when we get to the end, it better be 1, right? Because we know if we do the sum of all the probabilities, it has to get to 1. We agree? Sometimes you will see this given to you as a graph. So in this case, change colors here. Up until 0, it was 0, right? Let me put some more scale on this thing. Okay. And then at 0, it jumped to 0.2 until we got to 1. Right? We agree? And then it jumped to 0.3 until we get to 3. It jumped to 0.8 until we got to 7. And then jumped to 1 and continued on. So this would be a graph of your CDF. It's important to know when you're asked problems, especially if you're given a graph like this or a piecewise defined function like this, it's important to know, did they give me the CDF or did they give me the PDF? Because they have different information, right? You can get one from the other, but it's important to make sure you read it closely and make sure you know the difference. Because notice, these values that we've drawn are cumulative probabilities, not each probability, right? Where we see the probabilities in this case are the heights of the jumps. We see from this jump that the probability is 0 at 0. We see from this jump that the probability is 0.1 at 1. We see from this jump that the probability is 0.5 at 3. We see from this jump that the probability is 0.2 at 7. Does that make sense? So for the discrete probabilities, the jumps are your probabilities. Where there's a jump, is a probability. Anywhere where the CDF is flat, there's no probability. It's 0. Right? For discrete ones, it's just where the jumps are. Does that make sense? Now for continuous distributions, the graphs of your CDFs will be continuous. That's why they use the name continuous distribution. Because it accumulates probability continuously. Discrete distributions, it's not. It's got these jumps in it. And that's where the probabilities are, where the jumps are. Questions on that? Yeah, Megan. I got the name right this time.
For the 0, do you have to draw the arrow that way, even though x is less than 0?
I'm just drawing the arrow that we know that anywhere over here, the cumulative distribution function is 0 there. Oh, wait. Was that what you were asking about the 0? Okay. Yeah, I'm just drawing it so that I know that it's less than 0. It's always 0. I mean, it's not a very important part of the graph because it's going to be 0. But any other questions on that part? All right. So let's talk about two very specific distributions that we'll do some more problems with next time. One of them is referred to as the uniform distribution. And the other one is what's referred to as the exponential distribution. And this is section 3.4 in your text. So, uniform distribution, we've already talked about uniform distributions in the discrete sense. Flip a coin, you get heads or tails, it's equally likely, so it would be 1/2 for each of those possibilities. Roll a die, numbers you can get are 1 through 6, each of those are equally likely, so you have 1/6. Just take the number of possibilities and put 1 over, right? Right? So for uniform distribution for a continuous idea, it's the same idea. So for a uniform distribution, we say that x is uniform on the interval from A to B. And the endpoints don't really matter. You can put brackets on your A and B or parentheses. Because remember again, for a continuous distribution, the probability that you're at a specific point is 0, right? Okay? X is uniform on AB if its PDF is just 1 over B minus A. Oops. And 0 everywhere else. So it's 1 over the length of the interval. Which makes sense because think about it. What would your PDF look like if I did the graph of the PDF? I guess I had this. It would be a constant function, right? What does this area have to be under here for it to be a PDF? If it's going to be a PDF, what does that area that I just shaded in there have to be? 1, right? Because the integral has to be 1, correct? Well, then what kind of a shape do I have? It's a rectangle, right? So if this length is B minus A, what does this height have to be? They're going to have an area of 1. 1 over the B minus A, right? The height and the length have to be reciprocals of each other to get the area to be correct. Right? And the idea here is that we've got this basically what we refer to as a uniform density, right? There is not any more likelihood that probability is going to pile up on one end as the other. It gets spread out over the entire region. It's crazy.
Are we talking about discrete numbers here?
No, we're talking about continuous in this case. So any number, that's really shaky. Any number between A and B can get chosen. So it's going on any holes here. But again, we don't have like the PDFs that we saw yesterday or Monday. I mean, today is Wednesday, right? We had one of those PDFs where it piled up on one side, right? And so it was a lot more likely to get numbers on one side than it was the other. If you ran a simulation over and over and over and over and over again, you would get numbers that were spread out throughout the interval. They wouldn't be piled up on one side. Versus if I did a simulation with one of those other types of PDFs, the numbers I would pick would be a lot more piled on one side than the other. Because it was a lot more likely to hit ones over on the right side than it was on the left. So that's what we mean by uniform distribution. If you just start, for example, if there's a random function on your calculator, there's an RAND function where you can just do it and it'll put out a random number between 0 and 1. If you were to do that and just hit enter over and 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 over again, you would just get a bunch of decimals that are spread out from 0 to 1. There wouldn't be a whole bunch of dots. If you think about graphing dots, there wouldn't be a whole bunch of them on one side of the interval. They would get spread out pretty evenly if you did it enough times. Because it's a uniform distribution. Okay? For a uniform distribution, it's not hard to figure out what the cumulative distribution is. What kind of a function do you get if you integrate a constant? What kind of a function do you get? You get a line, right? You get an x, don't you? In fact, your cumulative distribution function here will be 0 if x is less than or equal to a. It'll be the line x minus b over b minus a between a and b. And it'll be 1 once you hit b. So you'll get a graph that looks like the following. That's what the graph of the cumulative distribution function will look like. It's not too hard to show that, right? Basically, what did I find? I found the equation of the line that has an x-intercept of a and goes up to 1 when I get to b. Right? That's all I did, isn't it? Check that pretty easily, right? If I put in A for x, what do I get? 0. When I put in B for x, what do I get? 1. That's all I did. That just gives me an equation of line that has A0 as an x-intercept and B1 is another point on the line. So that would be our graph of our cumulative distribution function here. Does that make sense? So, of course, with these distributions, one of the first things that we find out, of course, are its mean and its variance, right? Well, these aren't hard to do because it's an easy function to integrate. If I want the mean, if I would do the expected value of x, that's integrate over the support of x times the PDF. That's how we find the mean, isn't it? Well, this is just a constant. What can I do with the constant? Pull it out. And I just need an antiderivative for x, which is x squared over 2, right? Agree? So this becomes 1 over b minus a, x squared over 2, evaluated from a to b. Put in b, you get b squared. Put in a, you get a squared. So you get b squared minus a squared on top. B minus a on bottom. Any simplifying we can do? Probably wouldn't have asked the question if the answer is no. That's a difference of squares, isn't it? How does the top factor? B minus a and b plus a, right? So your b minus a's will cancel, and this will turn out to be a plus b over 2. Let's think about this for just a second and see if this makes sense. The distribution, the numbers are uniformly distributed from a to b, right? So if I wanted the mean or the expected value, it makes sense that it should be halfway in between the endpoints. It should be the average of the two numbers, right? If I think about them being uniformly distributed, if I just pick numbers over and over and over and over again, we would expect half of them to be below halfway, half of them to be above halfway, and evenly spread out. So if I average it out, it should be right in the middle, right? The whole point of being a uniform distribution. We would expect it to be in the middle. We can also do the variance. Of course, to do variance, I need to do expected value of x squared. And I know I'm going to do this one quickly, just because I'm almost out of time. When I anti-differentiate the x squared, we'll get x cubed over 3. So you'll get b cubed minus a cubed over 3 times b minus a. However, the top is also a difference of cubes, right? So if I factor the difference of cubes and cancel, I'm left with that expression. Right? Difference of cubes and factor is b minus a, and then b squared plus ab plus a squared. Okay. That's not the variance, though. What do I have to do to the expected value of x squared to get the variance? Yeah, subtract the expected value of x quantity squared. So I have to take the a plus b over 2 and square it. Right? Yes? So, yeah? Okay. Then if I want to combine these things, I need a common denominator, don't I? 6 will work. Multiply the first one by 2 and the second... no, 6 won't work. Try again. 12 will work. Multiply the first one by 4 and the second one by 3. 4a squared minus 3a squared gives me a squared. 4ab minus 6ab will give me a minus 2ab. 4b squared minus 3b squared gives me a plus b squared. The denominator was 12. And lo and behold, the top actually factors, doesn't it? I'm going to write it reverse as b minus a squared over 12. It's only because the b is bigger than the a. It's the only reason why I flipped it around instead of a minus b. So there's your variance for the uniform distribution.
Do we need to know the stuff for exam?
You'll need to know the mean and the variance, yes.
So all this continuous distribution stuff.
Yeah, it'll be at the exam as well. Yep. I mean, we got more to do after the exam.
Yeah.
It should, this is the last section that'll be covered on the exam.
You have some review guide on
It's already on the,
Oh, yeah.
it's already up there. So this is the last section that we'll cover for the test. All right, so we'll do more problems. We'll do actual problems tomorrow. I'll talk about the exponential distribution as well. Do problems tomorrow. Friday, review Monday.
So the times so like all the continuous ones are okay, so this is like a separate
No, we all have a PDF. And
okay.
that's how we find it. We just integrate the PDF.
Okay. So then like we're still using like binary values. Like
Continuous means that when I have the support, I've got intervals that I can choose from, not just a specific value. So like we had the binomial, you were looking for number of successes. So you could have 2 successes or 4 successes or 9 successes, but you can't have 3 and a third successes. So for continuous ones, one of the first ones that we're going to do Friday is the exponential one. We can think of exponential as waiting time until something happens. Well, something might happen in 3 seconds, something might happen in 5 seconds, but something could happen in 4.2 seconds, or a square root of 7 seconds. So that's a continuous idea. So the idea is that the values that your variable can take on are infinitely divisible.
so that's why we're doing the intervals.
High level fact.
Yeah, that's why we have the numerator.
Okay, so when we're doing these probabilities, it's probability that the event will fall in those.
Yep. Yeah, because if the probability is actually even with something, it's always zero.
Right, the chances of that. Okay.
Right. Because you're trying to pick one thing out of infinitely many.
Right. Okay.
Yeah.
I may try